Previous class, we obtained the line voltage waveform for 180-degree mode of operation. So it's a quasi-square waveform. It consists of each pulse. The width of each pulse is 120 degrees. So let us decompose this waveform into its Fourier components. So this is the waveform. So this is 30 degrees, and this is 150 degrees, and this is 210 degrees, and this is 330, and we have this 360 degrees here. So one complete cycle. It's magnitude plus Vs, and this is minus Vs. So it's starting from 0. Right. So you can consider the reference as this waveform. So we have, if you convert this into Fourier components, so this is VAB, right? So VAB of t, so this can be written as VDC plus sigma n equal to 1 to infinite an cos n omega t plus bn sin n omega t an cos omega t plus bn n sin omega t. Clear? So if you consider this is the reference, so this is waveform is symmetric, quarter-wave symmetry, so that means this value is 0. If you consider this is symmetry, if you consider this is the reference, in that case, so these cos terms are 0, right? So these cos terms are 0. Or if you consider this mid of this pulse as the reference, so this is the reference, in that case, the sine terms are 0. Otherwise, so Bn is 0. So consider this is the reference. So this one is the reference. So An is 0 and Bn. So what is Bn? So what is Bn? So it will be 1 by pi integration of 30 degrees to 150 degrees. Its value is Vs d omega t plus integration of 210 to 330 degrees, and its value is minus Vs d omega t. Agree? So what is this value? You can convert it into radians. You can convert, this is pi by 6, and this is how much? This is 5 pi by 6, and this is 7 pi by 6, and this is 11 pi by 6. So if you do this, so you will get 4 Vs by n pi, 4 Vs by n pi into sine n pi by 2 into sine n pi by 3. Right? So this is for n varying from 1, 2, 3, and so on, right? Yeah. So this is the value of Bn. So if you substitute n equal to 1, so what you will get? If you substitute n equal to 1, it will be Vs by n, right? Pi sine pi by 2, so that is 1 into sine pi by 3. Sine pi by 3. So we have the sine omega t. That is its coefficient, plus substitute n equal to 2. So if you substitute n equal to 4 Vs by 2 pi into sine 2 pi by 2, so that is sine pi. So sine pi is 0. So that means for 2, its value is 0. Similarly for 4, 6, 7, so that's value is 0. In other words, all the even order harmonics are 0 because the sine n pi by 2 is 0. So next we have n equal to 3. So here 4 Vs by n pi sine 3 pi by 2 into sine 3 pi by 3. So n equal to 3, right? So 3 pi by 3 again sine pi. So its value is 0. So that means the second order and third order harmonic is eliminated. And next we have fourth order. So that is also eliminated. So next term is n equal to 5. If we substitute n equal to 5, it will be 4 Vs by 5 pi into sine 5 into pi by 2 sine n pi by or 5 pi by 3. So what is this value? 4 Ps by 5 pi into sine 5 pi by 2. What is sine 5 pi by 2? What is sine 5 pi by 2?
1, sir.
So it is 1, right? Okay. So you left with sine 5 pi by 3 into sine 5 omega t. Agree? Similarly, the 6 is absent. So that means it is 4 Vs by 7 pi sine 7 pi by 3 sine 7 omega t and so on. So what is the exact value of sine 5 pi by 3?
Minus 0.866.
Minus 0.866, right? And this one 7 sine 7 pi by 3
0.866.
0.866, right? Clear? So that means clearly, so this value is negative. So this is negative and this one is positive. So this entire thing is negative, right? And this entire thing is positive. Okay. So that means this is moving in the clockwise direction. So this is moving in the that means the fifth order harmonic is moving in the anti-clockwise direction. And similarly, seventh order harmonic moving in the clockwise direction. So this you might have studied in the electrical machines. So particularly when you are studying the induction machine. So induction machines, we have some slots. So the slots are angled by 30 degrees, right? You remember that. If those are angled by 30 degrees, all the triplet harmonics are eliminated. And the MMF shape will be like this. So this is the shape of MMF in the air gap. So why exactly that is 30 degrees shifted? So why exactly that 30 degrees shift is there? So because to eliminate this third order, this sixth order, ninth order harmonics. So that way you left with fundamental, fifth, seventh, 11th and 13th and so on. So this is producing the torque in clockwise direction, for example, and the seventh order will produce in the anti-clockwise direction, right? Similarly, for the 11th order, if it's produced in the clockwise direction, so this will produce in the anti-clockwise direction. It's clear? So what you understood that? So three-phase inverter. So when it is operating in 180-degree mode of operation, so it is producing a quasi-square wave, and so it has a fundamental 5th, 7th, 11th, and 13th order harmonics. All the triplet harmonics, say 3, 6, 9, 12, and so on. So those are eliminated. In case of square waveform, so in that case, so you have all the triplet harmonics are present, right? Okay. So this is the fundamental. Okay, so this is the fundamental. What is fundamental? 4 Vs by n pi sine n pi by 3. So this is fundamental, right? Sine omega t. Plus we have harmonics. So what is its RMS value? What is the RMS value of the fundamental? So this is its peak value, right? If you know the peak value, so what is its RMS value?
2.78.
4 Vs by pi sine pi by 3 divided by root 2. So what is this
Root 2.
value? So what is this
0.78.
value? 0.78, right? 0.78 times Vs. So this is 0.78 times Vs. So this is VAB fundamental RMS. So this is VAB, so that represents the line voltage. So this one represents the fundamental and this represents the RMS value. So VAB 1 RMS. So this is equal to 0.78 times Vs. So what is the overall RMS value? So what is the RMS value of this waveform? What is the RMS value of this waveform? This complete waveform. What is the RMS value?
Vs root over
This
of
is
2 by 3.
120 degrees it is conducting, right? So out of 180 degrees, what is its RMS value? Will it be like this? Square root of 120 degrees by 180 degrees into Vs. So what is this value? Square root 2 by 3 Vs. Agree?
Yes, sir.
So this is the fundamental RMS value. So this is the overall square wave or the quasi square wave RMS value. So now how to find THD? What is formula for THD? VAB RMS by VAB1 RMS square minus 1, right? This is the one. So find out. So this is root 2 by 3 Vs by 0.78 Vs square minus 1. So what is this value?
30.73.
30 point, in terms of percentage, it is 30.73
73.
percentage. So this is its THD, right? So if we have the harmonic spectrum, so this is the harmonic order is increasing. So this is the magnitude. So we have this fundamental here. So if we assume this is fundamental is 100%, right? In terms of Vs, right? In terms of Vs, so what is this fundamental value? So this is 78%, right? In other words, so this is 0.78. Agree?
Yes, sir.
Okay. So what is the third order harmonic? So we have here, right? So what is this magnitude? No, third order. This is fifth order harmonic. What is this magnitude?
0.156.
So this is fundamental is 0.78, right? Okay, this is the fundamental RMS value is 0.78. So what is the third order harmonic magnitude? So this is 0.78 by 0.333, right? Agree? Similarly, we have the seventh order harmonic, so which is 0.78 by, so roughly 0. That is 100 by 7. So this overall THD, so that will be 30.73%. That is 30.73%. So this is in terms of Vs. If we assume that the fundamental is 100%, if we assume that the fundamental, this itself is 100%, so in that case, this is 33.3% and this is 100 by 7%. Both are same only. Only the difference is the y-axis scale. So when compared to the full square single phase inverter output voltage when it is operating at fundamental frequency, so where we got around 48% THD, right? So now because of the absence of triplet harmonics, the THD is come down to 30.73. Clear? Right. What the thing you need to remember is, so this one, What the thing you need to remember is this and this one, right? So what is this? So this is the, if you have Vs, right? For example, you have 1000 volts is there. Vs is 1000 volts. You are operating the three-phase inverter in 180-degree mode. So that means the fundamental, so line voltage is 780 volts. So this is the maximum voltage that you can obtain from the three-phase inverter. So meaning is, so this is the maximum voltage so that you can obtain from the three-phase inverter. So that is 0.78 times Vs. So for example, you are designing a 415 volts three-phase inverter. This 415 volts is the line-to-line voltage fundamental, right? Line-to-line voltage fundamental. So how to select Vs is, so 415 volts by 0.78. So that is the value of Vs. If you have this much of DC voltage, so then you can obtain a 415 volts. Then you can obtain a 415 volts fundamental waveform in the output voltage. That is the minimum value that's required. So remember, we are operating. This is the maximum value, so that obtained from the three-phase inverter, right? Irrespective of any model, either if you are using a Sine PWM techniques, in that case you will get lower value. If you are using a that means SVM space vector also, so that in that case also you are using a lower value of this.
Hello, sir.
Yes.
Sir, for harmonic spectrum, for fifth harmonic, why you divide by 0.33?
So this is the
For
fundamental, right? This is the fundamental RMS value.
Yes.
So with respect to fundamental, this value is 0.78 times 333, right? No, not 3. This is 5, right? Sorry.
0.2, sir.
Yes, sir.
This is 0.2. This is 0.2. Change it. This is 20% only. I am under the assumption that that is third order harmonic. So this is divided by 0.2 only. Right.
So multiply or divide, sir?
Divide. Second. This is 0.78 times, right? In other words, 0.78 into 0.8. And this is the correct representation. 0.78 into the remaining, that is point. No.
By 5 or into
So
point?
this
Sir,
is
0.78 by 5 we can write. Sir.
0.78 by 5.
5.
Yeah, this is 0.78 by 5. Yeah, this is correct. Okay. 0.78 by 5. In other words, 0.78 into 0.2.
Yes, sir.
Make the change here, that is 0.7. In other words, this is the best way. So assume that the fundamental is 100%. So this will be 100 by 5. So this will be 100 by 7, likewise. So any questions? So you have to remember this value. So that is 0.78 times the fundamental. Okay. So next we have, so if we assume that,
Sir, one doubt, sir.
yes,
Fifth harmonic magnitude is negative, no, sir. We can take it for sure.
that is magnitude, no? Right.
Yes, sir.
That's why you cannot represent the negative values here in spectrum.
Yes, sir. Okay.
Okay, so that's magnitude only. The only thing that is rotating in the counterclockwise direction.
Counterclockwise direction.
That's the
Yes,
thing.
sir.
Okay.
Okay, sir. Thank you.
In that case, the phase angle, you may get negative values.
Yes, sir.
So one is rotating at minus omega, one that is rotating at minus omega t. So next, what we have is how to obtain the phase voltages. So how to obtain the phase voltages. So as we already discussed that for two-level inverter or the three-phase voltage source inverter, so we cannot obtain the, for this inverter, we cannot obtain the phase voltage So you cannot obtain the phase voltage. That phase voltage is only obtained from the load. So let us assume these are the inverter terminals. So this is A, B, C. These are the inverter output terminals. You can connect some load here. This load may be connected in star or connected in delta. In case of delta connection, the phase inverter phase voltages and line voltages both are same. See, if you assume this is the load neutral, so this is load neutral, right? So this voltage between this A and N is the load phase voltage or inverter load phase voltage. So generally, so this is not at all importance. So how this load phase voltage is there, so that is not at all important. So remember, for 3-phase, so we are always interested in the line voltage. But this is especially important when you are deriving the space vectors. So space vectors are derived so based on this only. Okay. So line voltages are only we are concerned. We are not much interested on phase voltage unless so there is an unbalance in the circuit. Unless there is an unbalance in the circuit, so then only we worry about the phase voltages. Okay. So we have different modes of operation, right? So this mode 1, you're aware of these things, right? So in mode 1, so this is mode 1, right? So which devices are in conduction? In this mode 1, this 5, 6, 1 are in conduction, right? So 5, 6,
Yes.
and 1 are in conduction. So if this 5, 6, 1 are conduction, so this 1 is A phase positive, right? So this 5 is C phase, the C phase positive terminal, right? And the 6 is negative terminal. So from this you can see. So where you have this 5, so this is 5 here. No, this is 5 here. So this is your 5. So this is 6 and this is 1, right? So this 5 and 1 are connected to positive terminal. So whereas the 6 is connected to the negative terminal. This is connected to the positive terminal. This is connected to the positive terminal, right? So whereas the 6 is connected to the negative terminal. So this is its equivalent circuit, right? So this A phase, so that is C phase, are connected to the positive terminal of the DC bus. So this is C phase and this is B phase and this is A phase, right? So A and C are connected to the positive terminals, whereas B is connected to the negative terminals. So this is N. Okay. So you can find out the voltage between this A and N. So you can find out the voltage between A and N. So what is A and N voltage? Simply we can apply simple KVL or KCL. So this is, you can current, it will split the current. So it is I by 2 and this is I. So from that you can obtain the currents. So if you do this, so you'll get this value. You have already studied this, right? I'm simply skipping this. So this is the value for VBN. So Y minus, because the current is flowing in this is carrying the written current. So that's why for B phase, so this is minus. And similarly for A phase, this for C phase, so this is positive. So this is for mode 2. So mode 2, 6, 1 and 2 are in conduction, right? 6, 1, 2 are in conduction. This 6 belongs to B phase. So this is A phase and this is C phase. The 6 is the lower switch, so that's why it is negative. So this is positive, this is negative. In other words, B and C are connected to the negative plates. So B and C are connected to the negative plate here, and A is connected to the positive plate. A is connected to the positive plate. So that's why if you do this, so VAN is like this. So VBN is still minus, right? And here you have this. Okay. So both are carrying the written current in these two. So that's why you have minus sign. So if you continue this one, so here this magnitude is Vs by 3 and here this 2 Vs by 3. Clear? So this is how the load phase voltage is generated. So this is how the load phase voltage is generated. So remember these things. So we will use these things at the later point of this course. So next we'll move to the PWM technique, especially the sine PWM technique. So for this inverter, so how to control the inverter voltage if you are operating in the fundamental frequency mode? So how to control that? So only way is to control the width of the pulse, right? So only way to control is width of the pulse. So when changing the width of the pulse, still the harmonics are present. So in that case, we have to use it single pulse with modulation or multi-pulse with modulation. In case of single pulse or in case of multi-pulse with modulation, the width of the pulse is same. Therefore, the harmonic cancellation is very less. So that's why we'll go for sine PWM technique. So this is the sine PWM technique. So this is sine PWM. You know how to do the multiple pulse with modulation, right? So instead of comparing with a sine wave, so you will compare with a DC reference. So instead of that, so you will compare with the DC reference. So when you are doing so, the width of each pulse is remains same. The width of each pulse is remains same. So that means what the observation is that when the width of the each pulse is varying, so then only the harmonic cancellation is better. So now we have this sine PWM technique. So these are the carriers. These carriers, you have only one carrier, and these carriers are compared with a reference modulating signal. So here you have three phases. So that's why each phase is modulated by one modulating signal. So this is A phase modulating signal, and this is so this is B phase modulating signal, and we have this C phase modulating signal. This A phase, B phase, and C phase modulating signal. We have three switches, right? 1, 3, 5, or 6 switches, 4, 6, and 2. So this is controlled by A phase modulating signal, and this is controlled by B phase modulating signal, and this is controlled by C phase modulating signal. So when the carrier is above the when the modulating signal is above the carrier, upper switch is on, so S1 is on, otherwise S4 is on. The same thing is practiced here. The same thing is practiced here. So we have this VAN, right? So what is VAN? So this is V and this is AN. So this is positive DC bus and this is the negative DC bus. Okay. So VAN, this line voltage can also be obtained by this is VAN minus VBN. Okay. So this gives you VAB. So this is A phase, right? When the switch is on, right? When the upper switch is on, so VAN is VAN. So when the upper switch S1 is on, so in that case, its value is VS. So when the bottom switch is on, so its value is 0 when S4 is on. So that means the VAN is changing between VS to 0. Similarly, this VBN is changing between VS to 0. So we already said that. So that's why it is known as two-level inverter. So we have two voltage levels in the pole voltage or the terminal voltage. Right, but in the line voltage, we have three voltage levels, VS, 0, and minus VS. So usually formula is when you have two levels in the power in n levels in the phase voltage, in that case you have maximum of 2n minus 1 levels in the line voltage. So that means you have two levels here. So that means 2n minus 1, you have three levels. So this is the maximum levels. Maximum 2n minus 1 levels. So we have detailed discussion on when you are discussing the other inverter topologies. Right. So this is how we will obtain VAB. So upper switch is on, its value VAN is 0, and the lower switch is on, its value when the upper switch is on, VAN is VS, otherwise its value is 0. Yeah. So this is VAN, right? Similarly, at the same time, this is VBN, and the difference between VAN and VBN. So this is the difference between VAN and VBN. So here you have this line voltage. So here you have this line voltage. So when you are applying a sine PWM technique. So interesting thing is, so if you have modulation index MA equal to 1, right? If you have modulation index MA equal to 1, if you are using a sine PWM technique, so in this you have, inside this you have this fundamental, right? So this fundamental, VAB fundamental, RMS value is 0.612 times VS. So that meaning is, so this is the maximum value of fundamental, so that you can obtain from the sine PWM technique. So overall maximum is 0.78 VS, right? So that is when you are operating with square wave or the quasi square wave. But when you are using a sine PWM technique, right, when MA equal to 1 or the maximum modulation index, so from that you can obtain the value of, from that you can obtain the maximum value is 0.612 times Vs. Right. So we have two inverter designs, right? One, we can operate the inverter in quasi square wave, or we can use a sine PWM technique. So this is better, right? Sine PWM technique is always better because the harmonic cancellations or harmonics are moved to the higher side. So meaning is same thing. If you have 415 volts inverter, so when you are using a square wave, so it will be, the VDC will be, so 415 volts by 0.78 in the first case. And in the second case, right, this is quasi square wave operation. In case of PW sine PWM operation, so the maximum value is 415 volts by 0.612. So based on that, the DC voltage will be selected. It's clear? Right. So here, so we have the operation is something like this. So you have this MA modulation index, right? And here the output voltage. So from 0 to 1, right? So from 0 to 1 value of MA. So from 0 to value of 0 to 1 MA. So that is under modulation. So you know exact at what exact values the switching will take place, right? You know at exact values what switching will take place. For example, if this modulating signal is something like this, in that case, some of the pulses will be skipped, or some of the intersecting points will be skipped. So instead of getting these kind of pulses, you will get a large pulse, something like this, right? So in that case, so whatever that linearity is there, right? So that linearity will be lost. So that's why from 0 to 1, if this is the, or this is MA, right? So from 0 to 1, so here we have linear range. So what is this value? This MA equal to 1 corresponding to 1. For example, MA equal to 1. So what is this value? This is 0.612 times VS. Agree? So as you keep on increasing the modulation index, right? As you are keep on increasing the modulation index, right? So here, so up to here, this is linear. Right? For example, the meaning is, for example, you have operating at 0.5 MA, right? For example, that means the DC, the AC voltage is exactly half of that. That means you will get 0.306 VS when you're operating corresponding to MA equal to 0.5. So that means the voltage control is easy. So once it's gone to overmodulation, slowly it will be operate like this. It is operating in non-linear. Okay. So after it reaching certain value, right? So after it is reaching certain MJ value, so that means, so this is the maximum value, right? So this is 0.78 times VS. So here, even you are increasing this MA, so there is no change here. So that means it is constant. So even though you are changing this MA, so this is constant. So we have three modes of operation. So this is under modulation. So this is over modulation, and this is quasi square wave operation, or simply square wave operation. So this is linear range, non-linear range, non-linear range, and there is, so here there is no control of output voltage. So no control of output voltage. So even though, so you're increasing this MA, so there is no control over here. So usually, so we'll try to operate as long as possible, unless some fault conditions are there, or unless some unwanted unloading, unwanted overloading is there. So in that case, most of the cases we'll try to operate the inverter as close as possible to, or in other words, in under modulation only, because the output voltage control is easy. So when you have, sometimes if the load is suddenly increased or a sudden unwanted load is there, in that case we may go for over modulation for a slight duration of time. So this value is usually 3 per MF equal to 15, but this value is 3.24. MA value is 3.24. This per particularly MF equal to 15. So this value, so at what point, so it is drives into square wave operation, that all depends on the MF value. That is frequency mod, or that in other words, it depends on the carrier frequency. For MF equal to 15, so you have MA is 3.24. That means for MA 3.24 onwards, so this is drives into square wave operation. Clear? So next we'll study the harmonic spectrum of this waveform. So this is the harmonic spectrum of line voltage. Harmonic spectrum of line voltage. So this is particular for MF equal to 15. So at 15, 30, 45, and 60, so there is no harmonics. So only you have sideband harmonics. So this is 15, that means you have 13 order harmonic. So this is 17. So this is 29, and this is 31. Right. So this is 40, 43, right? And this is 47. So this is 41, this is 49, and so on. So this is corresponding to MF equal to 15. So you have no harmonics at MF, 2MF, 3MF, 4MF, and so on. But the sideband harmonics are presented MF plus or minus 2 plus or minus 1. We already discussed that. So this multiplication is, so this is this number, for example, this is 2 is, that is even number, you have plus or minus 1. If this is odd number, so you are multiply with odd number. So that means in that case, this will be the even number. If this is even, so this will be odd and separated by plus or minus 2, plus or minus 4, plus or minus 6, likewise. This clear? Since it is operating at, so here these bands are present. So what is the inverter frequency here? What is the inverter frequency? What is the inverter frequency? Based on this, we can identify the inverter frequency, right? What is the inverter frequency here?
150.
Carrier frequency. So switch frequency, so that is also equal to carrier frequency, right? Unless it is operating MA less than or equal to 1. So if it is over modulation, so in that case, the inverter frequency will come down, right? The switch frequency will come down. So why it will come down? Because it will skip some of the pulses. So that means some of the pulses are skipped, means the inverter frequency is also reduced. So when observing this harmonic spectrum, we can identify the inverter frequency, right? So next we have over modulation, so that we already discussed. So when it is above MA equal to above 1, right? For example, this case. So this is above 1, right? So here usually carriers are changing from +1 to -1. So this is above 1. So here you have some large pulse. You have some large pulse here. The good thing with this overmodulation is the output voltage in sine PWM technique, this is right. So this we can boost to 0.78 times Vs. The output voltage can be boosted to 0.78 Vs. In other words, so these all things are known as DC utilization. Meaning is how much DC you have or how much DC you are inputting and how much AC output voltage you are getting. Right. So that means, so how properly the DC is utilized. So that is important, right? So here, so in this case, if you are using a sine PWM, so the DC utilization is only 61.2%. So in this case, it is 78%. So the disadvantage with this DC utilization is it is producing the order harmonics, that is fifth order, seventh order harmonics. But this is good, right? Sometimes, so slightly we can go for this overmodulation. We can increase this one, so 0.68 to 78 times. For example, you have MA equal to 2. So in this case, these pulses are skipped. The disadvantage here is these lower order harmonics. Okay. So when you are operating in overmodulation, some of the pulses are skipped, some of the intersecting points are skipped. So therefore, when the pulses are skipped, so obviously it will affect the harmonic spectrum. So therefore, so these lower order harmonics are emerges. Clear? The disadvantage with overmodulation is lower order harmonics. The advantage is we can boost the output voltage from 0.612 Vs to 0.78 times Vs. So if it is completely, for example, as we discussed, if MF equal to 15, right? So this is 0.31. So instead of that, so you'll get a bigger pulse like this. So this is one single pulse. You have one single pulse. The width of this pulse is 120 degrees. So therefore, you have this fifth order harmonic, 7th, 11th, 13th, and so on. This entire thing will not there. Right. So here this fifth order harmonic, 7th, 11th, 13th, and so on likewise. So that is a complete quasi square wave operation. Clear?
Yes, sir.
So instead of going to overmodulation, so there is another technique so that we can use or that we can boost the output voltage. So there are two methods. So one is the zero sequence injection PWM, zero sequence injection PWM, zero sequence voltage injection PWM. So another one is space vector modulation. So now we will discuss the zero sequence voltage injection PWM. So the idea is to increase the DC utilization without involving or without emerging the lower order harmonics. So we have this zero sequence voltage injection PWM, right? We have this zero sequence injection PWM. The idea is pretty simple. So we have this fundamental here. So this is the original modulating signal, right? We have original modulating signal. So for this original modulating signal, we are added a third order harmonic here. This is third order harmonic, right? So you have one fundamental, you have one cycle, second cycle, and this is third cycle. This is the third order harmonic. So we added a third order harmonic. The resultant, this is the end resultant waveform. So this is the resultant waveform. So if you notice that, so this waveform is slightly, right? So this is for limit, right? This is plus minus, this is the carrier limit, this is plus minus. So here this waveform is slightly over modulated. The original modulating signal is slightly over modulated. But as and when we are added a zero sequence component, so you can see that, so this is in the, so you can see this is in the limits of modulating cycle. So this waveform, especially the stop is changed like this. this top is changed like this. And so now it is, if you notice that this is not exceeding +1, right? Or this is not exceeding this line. So that means still it is in under modulation. Still it is in under modulation. So what is the difference here is, right? So when you compare these two waveforms, so this is the voltage lost, right? So this is the voltage lost, but this is the voltage gain. So this much is the voltage gain here. So if you integrate this, so those two things will be same. So due to introduction of this, or due to addition of this zero sequence component, so this is the voltage loss to keep that under modulation. But if you notice that the shoulders, for example, the shoulders are slightly widened, right? When the top is slightly reduced. So what is the thing when the shoulders are when this is brought? So instead of with the sine wave, so in that case the width of these pulses will change. So this one original, right? So what is the advantage here is, so width of these pulses are changes. So here there is a slight change in the width of these pulses, because it is having a longer duration. Means this is having some longer duration. So when compared to this one, so therefore the width of the pulses are changing. So when the pulse width is changing, means the output voltage is also increasing. The output voltage is increasing here. So here the thing is that this one is there, right? So here this is slightly increased. So that means that this width is slightly increased. All these pulses width will be slight increase. If there is increase in the slight increase in the width, so that means the output voltage will be increased. Clear? So this is known as zero sequence voltage injection. So you can see here. So this width is slightly increased. So when compared to the original Sine PWM technique. When compared to the original Sine PWM technique. So the advantage with this one is, the advantage with this zero sequence injection is no. So that means lower order harmonics are not injected. Right? The problem with this overmodulation is the lower order harmonics, right? So that problem is solved. Another thing is, so how much you can inject. So how much you can inject is, right? So usually this is 10% or 15%. So based on that, so how we are operating. So here, thing is that, so from 0.6.2 times Vs, so you can boost up to 0.70 times Vs. You cannot completely boost to 0.78 times Vs, so which is not possible. So but using this zero sequence injection PWM, voltage injection PWM, so you can increase the DC voltage utilization by, so how much percentage, if you calculate in the percentage times, you can increase by 15.6%. That is 0.707 minus 0.612 by 0.612. So that will be 15.6%. This is very important. Most of the competitive exams, they will ask. Okay. So by using zero sequence voltage injection, so we cannot completely achieve the square wave operation like overmodulation, but so we can without increase, this is without increasing or without going for overmodulation. Okay, so you are keep on increasing this zero sequence. Sometimes it will cross the sometimes it will go to overmodulation, right? So without overmodulating the overall this waveform, without overmodulating this waveform, so you can obtain a maximum voltage of 0.70 times Vs. So which is a 15.6% of this. So when you are injecting this third order harmonics, right? So we are injecting in the phase voltages or the phase voltage modulating signals, right? So that means in line voltage, so these are free from, so you have doubt that we are injecting some third order harmonic likewise, right? So whether these harmonics will exist in the line voltages or not. because we are injecting only in the phase voltages, right? But the line voltages are free from this third order harmonics, whereas you have other phases are there. So in that case, A phase voltage and B phase voltage, so those two will be cancelled, and the line voltages are free from this third order harmonic or this zero sequence harmonics, are free from this zero sequence harmonics. Right. So this is A phase, right? So when you are injecting a zero sequence component, so we have to make sure that, for example, if a B phase is there, so that means for B phase, it should start from, it must be synchronized. So A phase, this zero sequence harmonic, the third order harmonic and the fundamentals are synchronized, right? Similarly for B phase, so that is synchronized. For C phase, so that must be synchronized. So when you are injecting, so it must be synchronized way. And we have to make sure that, so the overall waveform or the overall modulating signal must be in the limits of modulation range or 0 to 1 range. And one thing I forgot to say. So this is, we already discussed the synchronous PWM and asynchronous PWM, right? So this is A phase, right? So this is A phase modulating signal. This is started at 0, right? Similarly, if the B phase, so that must be started at 0. In B phase also, if the B phase is going like this, the triangle carrier must be something like that. It both must start from origin, for example, right? Similarly for C phase, so that should be also start from origin. If you want this, so in this case, so this MF must be divisible by 3. So MF must be divisible by 3. In other words, we need to choose the MF value 15, right? 15 or 21, something like that. So this MF must be divisible by 3. That is one reason to have a synchronous PWM. To have a synchronous PWM, this carrier frequency must be divisible by 3. So that all the phases will be having this synchronous PWM, or the carriers and modulating signals are synchronized. And another one, so this MF must, you must choose MF value as odd number. So this MF must be odd number. For example, you have 20 is there, right? So in that case, MF is 20. So in that case, you have 15th order harmonic and 22 order harmonic. So this must be avoided, right? So this MF must be odd number, right? MF must be odd number. If MF is less than 21, right, we have to make sure that, so this MF is divisible by 3. So that we have synchronous PWM. Clear? So MF must be odd number, and this MF must be divisible by 3. So when you want synchronous PWM, so this, we already discussed that MF is greater than 21. So whether it is synchronous or asynchronous, there is much difference. The performance is more or less same only. Yeah. So this is about the different PWM schemes, so that are used for the single phase and 3 phase inverters. So next class we'll discuss about the, what to say, selective harmonic elimination. So we already studied that selective harmonic elimination.